Welcome to the first episode of this series, An Introduction to. In this series, we scratch the surface of interesting technologies and concepts, new and old. In this episode, we are going to talk about ReasonML, the language ReasonML, which isn't actually a language, but we'll get to that in a moment. So we are here at the GitHub Pages page of the ReasonML project. And let's just read this introductory text here. It says that Reason lets you write simple, fast, and quality type-safe code while leveraging both the JavaScript and the OCaml ecosystems. So somehow we get to leverage both the ecosystem of JavaScript and the ecosystem of OCaml. JavaScript you all probably already are familiar with, but what is OCaml? So OCaml, originally named Objective-Caml, is the main implementation of the programming language Caml, created by this set of people. The language is a member of the ML language family, and this is why Reason is called ReasonML, I assume. So OCaml extends the core Caml language with object-oriented programming constructs. But let's not dig down too far in OCaml, but let's just first mention that OCaml first appeared in 1996, so that's quite some time ago. But either way, before we jump back to Reason, let's just quickly look at the philosophy here. So ML-derived languages are best known for their static type systems and type-inferring compilers. And this is something that we see in Reason as well. OCaml unifies functional, imperative, and object-oriented programming under an ML-like type system. Thus, programmers need not be highly familiar with the pure functional language paradigm to use OCaml. So, OCaml mixes functional style and imperative style and object-oriented style. So in some sense, you can get the benefits of pure functional programming without the constraints, because you can be pragmatic and drop down into imperative programming, programs that mutate state whenever you need to. And we'll come back to these points when we look at the philosophy of Reason. But let's jump back to the Reason page. So ReasonML, I guess, is one of these projects that realized that we need to compile to JavaScript because JavaScript is an extremely universal language. It essentially runs in every browser. However, we might not want the downsides of JavaScript. We might not want to have to write JavaScript for reasons such as, for example, dynamic typing. We might want a more proper type system. We might want stronger typing. And thus, we can use OCaml. And then there's this thing called BuckleScript. So this is the GitHub Pages page for BuckleScript. And BuckleScript essentially compiles OCaml to JavaScript, and Reason is based on BuckleScript. So BuckleScript takes OCaml code and compiles it down to JavaScript. However, the people who constructed Reason realized that maybe the syntax of OCaml feels too esoteric for people who are familiar with languages such as JavaScript or come from languages such as Java or C#. And so if we construct an alternative syntax that first compiles to OCaml and then compiles to JavaScript, then this new syntax can be more similar to JavaScript, and thus it would be easier to achieve adoption. So if we look at the docs here, and if we go to the what and why page, we can see that this basically is the way that they describe it. Reason is not a new language, and this is back to the point about it not being a language. It is a new syntax and toolchain powered by the battle-tested language OCaml. Reason gives OCaml a familiar syntax geared toward JavaScript programmers and caters to the existing NPM and Yarn workflow that folks already know. So Reason essentially gives us an alternative way of writing OCaml code that is more familiar to those of us who are not familiar with OCaml but are familiar with JavaScript. So we get the benefits of something that looks kind of like JavaScript. However, we also get the benefits of OCaml, such as static typing and type inference. And then using BuckleScript, we can compile this OCaml code down to plain JavaScript and then ship our application to any web browser in the world, because almost all web browsers run JavaScript. So let's look at the why section here, and let's look at these two top points. So using Reason, you get a rock-solid type system. in their words. And then they explain that OCaml types have 100% coverage. In other words, every line of code. Inference, in other words, the notion of type inference, the idea that you don't have to explicitly specify all the types. Instead, the compiler can figure out what types things have by inferring. So you don't always have to say that this variable contains a string. For example, if you declare a variable and put a literal string inside of it, the compiler will understand that, okay, this variable will have to be a string, and then you don't have to explicitly specify it. So OCaml types have 100% coverage and soundness, which means that when it's compiled, the types are accurate. The second point here is an eye for simplicity and pragmatism, and that's back to the point of OCaml. So they explain here that we allow opt-in side effects. In other words, you can choose to use side effects if you want to. You can choose to mutate if you want to. And they do this for familiarity and interoperability. So interoperability in the sense that if you want to use external JavaScript libraries, then these might already be mutating. And if your program can't mutate, then you can't use external libraries that mutate. So in order for that to work together, or in order for your code base to be able to use all of the existing libraries, they need to allow mutation. But I think more importantly, in relation to what we looked at here with OCaml, it follows the light of OCaml. It follows the vein in which OCaml is designed, or it follows the philosophy of OCaml, because OCaml unifies functional, imperative, and object-oriented programming. So I may be mistaken on this, but my interpretation is that OCaml is not a forced pure language. You don't necessarily have to write pure functional code, but you can employ mutation if you want to. In other words, OCaml is too a slightly pragmatic language from that perspective. Moving back to the reason page, let's go back to the front page. What we didn't talk about before is this code example here on the front page. So you might be slightly familiar with this syntax, or this kind of syntax, if you're either familiar with functional programming or have used, for example, TypeScript and come across discriminant union types or algebraic data types. So this concept has many names, but what's really wonderful about this example, and this single example is really why I got really enthusiastic about Reason, because they say it's statically typed and they give us this example, and I got the impression that you could do composition and still maintain proper types. But anyways, about this example, what we do here is that we say that there is a type called school person, and this in TypeScript would be known as a union type, but in Reason they call it a variant. So this school person is either a teacher, a director, or a student that has a string. So presumably this string is the name of the student. But what this union type, or what this variant does, is that it says that we have the notion of a school person, and any school person must either be a teacher, a director, or a student. And if you're a student, you need to also have this string. That is like the contract of what it means to be of the type school person. Now, what's interesting about this is that we can define a function, and here they define a function that they store in the variable greeting. And this function takes a stranger. Now, this is the name of the variable, and notice that we are using implicit typing here because we are not specifying explicitly the type of stranger. But the point is that we take a variable which we refer to as stranger, and then the implementation of that function essentially is 4 alternative implementations, or entails 4 alternative implementations. Which of these implementations we will run depends on the kind of stranger that we are passed. So if we are passed a stranger which happens to be a teacher, then we respond with, or we return the string, hey professor. If it's a director, we return hello director. And if it's a student that happens to be named Richard, we return still here Ricky. And if it's a student that has a name that doesn't match the string Richard, then we respond with hey, and then concatenate that with a name and a dot. So through pattern matching, we can define different implementations depending on what we are passed, or what we are passing to this greeting function. So notice that we are not only switching over or varying the implementation based on the type of this variable, we are also able to pattern match based on the value inside of this string. So notice the syntax here. So student here, apologies if my terminology is sometimes incorrect because I'm not super familiar with functional programming. But this, if I'm not mistaken, is known as a constructor. So directors don't necessarily contain any values. Notice that director does not have this parenthesis and then some kind of type. So directors are simply just directors, and teachers are simply just teachers. They are some sort of empty in terms of when we store a teacher inside a variable, all we know is that it is a teacher. We don't know any data. We don't carry any data around surrounding this teacher. However, to have a student, this student needs to also come with a string. So when we construct a student, we construct it with a string, and we would construct it in this fashion. But here we are pattern matching. Here we are saying that if I am passed a student whose name, whose string is Richard, then I want to run this implementation. And then here, in this case, we are not matching on Richard. We are simply matching on a variable. We're simply saying that if you have a student, then there will have to be a variable here, because the definition of a student is that there needs to be a string here. So let me refer to that as any other name so that I can refer to this variable within the implementation here. So any student that is not named Richard will not match this pattern. However, it will match this pattern. Note that Richard would of course also match this pattern. So if this matches first, then this will be ignored. Now, what's really interesting about this kind of pattern is that you can have a compiler that is exhaustive. So it can tell you whether you have exhausted all the options. In other words, it can tell you whether your implementation that will accept something of type school person actually has an implementation for all of the different cases that it needs. Imagine that you would remove this line. We just remove it. We remove this line that says that if it's a director, then we respond with the implementation hello director. If we remove that, that means that we have not specified what will happen if the greeting function will be passed a director. Which of course is a problem, because what happens if we pass a director? And so what's excellent about OCaml is then that the compiler will know that you've missed this case. And if you're familiar with TypeScript, we can achieve this in TypeScript by using discriminant properties. Let's try out some simple reason code. So let's click the try button here, and it takes us to this page where we can write reason code in this upper left box, which will then compile down to OCaml code in this lower left box, which will then be passed through BuckleScript in order to produce JavaScript, which will end up in this box, which then will be run and give us the actual output. Sounds silly, but let's look at it. So let's just do a JS log hello world. So JS log is the equivalent of console log in JavaScript. So you can see that this generates this BuckleScript code. In other words, since console log is a thing that's specific to JavaScript, BuckleScript needs to have something else because OCaml doesn't necessarily have the console log statement. So here it compiles to JS log. But this is essentially the BuckleScript equivalent of the code that we wrote up here, or the OCaml in the BuckleScript fashion equivalent of the code that we have up here. And then that's passed through the BuckleScript compiler in order to produce this JavaScript code. And then this JavaScript code is run in order to produce this output. But let's do something else. Let's just declare this variable called foo, and inside of it, let's throw the string bar. And again, you can see that the OCaml code is generated, we get some JavaScript, and then we get some output. But of course, now we're just declaring a variable, so there is no interesting output from running this particular JavaScript. And again, about the implicit typing, note that this is okay, even though we're not specifying the type of foo. So if we would explicitly specify the type of foo, we would say let foo of type string be equal to bar. And that of course works as well. It gives us some OCaml code. Now the JavaScript is the same, because JavaScript of course isn't typed. But because of type inference, we don't have to specify this, because when we specify that foo is equal to the literal string bar, the OCaml compiler will understand that bar is a string and thus infer that foo must be of type string. But let's look at some more interesting code. So let's look at the pattern matching example similar to what we had before, but using a different analogy. So let's say that we have a type called animal, and anything of type animal needs to be either a cat with a name denoted by a string, or a dog containing a string, or in other words, that has a name that is of type string. So we imagine that the string denotes the name. And now you can see that this is the OCaml or BuckleScript style code that's generated from this. Interestingly, we don't have any JavaScript yet because this is simply a declaration of a type which doesn't really make any sense, or of a variant type which doesn't really make any sense in JavaScript. But either way, we can now start to write that implementation. So let's say that we have a function which we want to call speak, and this function speak accepts an A of type animal. We're going to allow the compiler to infer this, so we're not going to specify that it is of type animal. But let's call this A, and we assume that it is an animal. But what's the implementation of this function? Well, this function, what we want to do is we want to pattern match. So we switch over this A. And what are we going to do with this A? Well, this A, we have a few cases to match for. So this A can either be a cat that has a name, and let's just respond with meow. So, by the way, I tend to write meow like this, but people have been telling me that this is not the way you write it in English. I assume that you write it like this instead. But anyways, we respond with meow, but if it is a dog, however, with a name, then we can respond with woof. And now you can see that we can compile again. We have some code here, and we now have some JavaScript because we now have an implementation for that, or we now have some actual code that could be run because we have a function definition. So let's try this out. So remember how I said that this means that we can construct a dog. So we can now construct dogs like this. So let's say that we have a dog called Whiskey, and we can construct a cat like this. Let's say that this cat is called Snuggles. And actually, let's uppercase the first letter of the word whiskey here as well, because it's a name. So we now have these two animals, but we haven't actually done anything with them. But what we can do now is that we can pass these animals to the speak method. You can see that this compiles just fine. But still, we are not actually printing anything from this. But we know that this will return a string because the type inferred of the function speak is that speak will take something of type animal and return a string, because all return values are strings. So what we can do is we can JS log this. So we log the output here and we log the output here. And now we can see that the two answers that we get are woof and meow. And this is because the first one is a dog and the second one is a cat. So let's add some more to the implementation here. Let's say we concatenate the contents of the name variable, in other words, the name of the animal, with this message that says and then meow. So name ++ says woof. So whiskey says woof is now the result, and Snuggles says meow. And now you can see that if we had another cat, which is named something else, well, let's say gato. So this gato says meow. But it gets the meow implementation because it's a cat, but we get the contents of the variable gato because that's the name of that particular cat. Now, of course, we can do what we did in that example, and we can pattern match on the actual contents. So let's say that we have a special case, which is that if the cat is gato, then we want to have a different implementation, and then we want to say maybe OMG, it's you again, gato. And then we can see that this should match any cat whose name is gato. But now we can see that we didn't get that implementation here, and that is because of what we talked about before. This pattern, a cat with any name, is more general than a cat named gato. So what happens is that we match this one before we match this one. And actually we get that as an error here, or as a warning. It says it's not an error because we did get to compile it, but it's a warning. It says that actually this match case is unused. So let's see, we get that on line 7, which is line 7 here, which is exactly the gato case. So what we need to do is that we need to take this gato case and place it before the general case for cats. And then we can see that when we pass gato here, we get OMG, it's you again, gato. And in the other cat case with Snuggles here, we get Snuggles says meow. So in the gato case, we match this gato pattern, but in the Snuggles case, which doesn't match the gato pattern, we end up in this case. And the awesome part about this is that it's all typed. And again, it's exhaustive. So if we remove, let's say we remove the dog implementation here, or the dog pattern, then we have a problem. It now says, warning, this pattern matching is not exhaustive. Here is an example of a value that is not matched. Dog, and this underscore means that there could be any value for this particular string. Actually, let's try and zone in on this one. If I go backwards, if I undo back to this implementation, and let's add a specific name here. So let's say that if we pass doggy, and then we add an implementation for that, like, yay, doggy, doesn't really matter. Then we can see that the error message is now actually slightly different. They show that here is an example of a value that is not matched, and we now get dog and then empty string. So I'm not 100% sure on how this works, but in some sense they're trying to give us an example of some of the cases that don't match. I mean, we could add the empty string case to this as well. Maybe the implementation is dog with no name, or we should say hello dog with no name. But then they give us an example of a value that is not matched, and then they give us this string containing an asterisk. So either they literally mean a string with an asterisk, or I assume they mean I assume they mean any string by using this asterisk. And that essentially is this case where we make the string that the dog needs to have into a variable, and then match regardless of what the contents of that variable is. And then we can again compile. Let me just sort out this implementation back to what we had before so it makes more sense. So a dog with name says woof. But that's that for pattern matching. And again, hopefully you can see how this is massively powerful since it's typed. Before we wrap this up, let me show you one more thing. What I found surprising about this is that, unless I'm mistaken, OCaml does not in the standard library have an implementation for the compose function, which you are probably familiar with if you either have worked with functional programming before, or if you have used JavaScript libraries such as Ramda, which we will probably talk about in some other video, by the way. But I want to show you how extremely simple it is to implement a very flexible compose function in ReasonML, or more specifically actually in OCaml. And let me just, for the sake of attribution, mention that the code that I will type out now I found in a StackOverflow thread, which I've linked in the description. But what is function composition? Remember that if we are composing the functions f and g, so I use the symbol O to denote function composition. So this is the composition operator. So if we have the function f and we have the function g, and we compose these together, and then I throw this parenthesis in to show that this returns us something, and that will give us a composed function to which we pass an x. So that would be equivalent to f applied to g applied to x. Now, if this sounds like Greek to you, don't worry, just ping me and we can talk about this some other time if you're interested. Function composition is really powerful, and I promise you it's worth digging into. But for now, let's just focus on how this becomes very easy in ReasonML or OCaml. Or I should say, how function composition is very easy to implement. So if we compose f and g, then the implementation we want is that when we pass x to the function returned by the composition of f and g, is that we want to first pass x through g, and then pass the result of that through f. Or in other words, we want to first apply the function g to x, and then apply the function f to the result of g applied to x. And this is actually really simple. So we just define a function. So let us just define a function, and let's actually call this function less than. And I'll show you why in just a moment. But for now, let me also emphasize that the reason we do this is that we want to actually define this function as an infix operator. So let's actually look at what an infix operator is, or infix notation. So infix notation is the notation commonly used in arithmetical and logical formulae and statements. It is characterized by the placement of operators between operands. In other words, infixed operators, such as the plus sign in the expression 2 plus 2. So if you think about it, plus here is the operator, and this 2 and this 2 are both the operands. So this is different. This notation style is different from what we usually do in programming. Usually when we run functions, we use prefix notation. We say plus, and then we pass the first 2, and then we pass the second 2. But infix notation is a very useful notation when we're expressing math, for example. So if you think about it in this way, if we have a function called f, and this is x and this is y, then instead of writing f parenthesis x comma y, we are simply saying x f y. So it's a slightly strange way of expressing this. And what's interesting about OCaml is that you can actually define functions as infix functions, or functions that are callable using the infix notation. So the reason I chose this less than sign to define this function is that not all function names can be used as infix functions. So here is a table of characters that we can use as operators if we want to define something which is callable using the infix notation. We don't have to dig into this now. I just wanted to emphasize this because I found it particularly interesting that you can actually define functions that are callable both using infix notation and prefix notation. And actually, when we talk about composition, it's fairly useful to describe things using the infix notation. Either way, we now define this function called less than, but I'll refer to this as compose. And what's the implementation of this function? Well, firstly, it needs to accept three things. It needs to accept a function f, a function g, and some x that we need to apply it to. And if you think about it, this is just, so what we're defining is this function, composition, and we need to accept an f, we need to accept a g, and we need to accept an x. And now we get to the really powerful parts of OCaml. OCaml, if I'm not mistaken, at least in Reason this is the case, all functions are auto-curried, which means that if you call this function and only supply it the first argument, then it will, in other words, you only supply it the f, then it will return a new function that accepts the g and the x. And if you then supply it only with another function, in other words, the g, then that will return you a new function that only accepts an x. And so forth, generally for all functions, which is fantastic, which is why we then can write it like this and still achieve composition, or still compose a function like this that we can put inside a variable, pass around, and then apply multiple times to any x. But let's write the implementation here. So the implementation here for this function is simply f applied to g applied to x. And let's terminate that line. So let's now demonstrate that this works. Let's define two silly functions in order to have something to work with. So let's define the function add1 that takes a number and simply adds 1 to that number. Let me actually call this variable x. And then let's add another function, let's call it double, which takes an x and then simply multiplies that x with 2, in other words, doubles that x. And what we want to do now is that we want to compose add1 with double. Actually, let me, instead of add1, let me call it inc, as in increment. And the point is that it matters whether we first increment and then double, or we double first and then increment. But what we can do now is, let's start by calling this the compose function using prefix notation. So we can call it and pass inc and then pass double, and let's call it all the way, and pass, let's say, the number 10. So it looks a bit funny because we have this strange symbol that represents the function, but just think about this as f. I mean, if we call this function, if we call the compose function, or sorry, let's say c, if we called it, or we could have called it compose essentially, then this is the way we would have called that function. But now we are calling this, we're giving it this funny less than name, and we need to use these parentheses in order for the compiler not to be confused. But we can then call this function and pass the function inc and pass the function double and then pass some particular x that we want to use. And if we jslog the output of this, you can see that we get 21. Because why? Because we first apply double and then we apply inc to the value x. If we look at this, right, that's the implementation. We first apply g to x and then we apply f to that result. So that would mean that we first do 10 times 2, but then we add 1. And that's why we get 21. Now, the thing I said about auto-currying is that what we could do is that we could have defined a new function. Let's simply just call it f. And let's say that this f will contain the composition of inc and double. And because of auto-currying, this means that f will now contain a new function where f is set to inc and double is set to g, but we are expecting another value, which is the value that we will use for this x variable, because that parameter, that argument has not been given yet. So if we then run f on 10, and then we JS-log this, you can see that we get the same thing. But now we can reuse this f function and run on 20, for example. Now, I don't want to drag us down the discussion of why composition is very useful. If you're interested in composition, ping me and then we can talk about that in other videos. But what I want to show you, however, is that the reason I defined the compose function like this, or again, why the person in the StackOverflow thread defined it like this, is that what we can do is that we can define another function which sort of points in the other direction, that is greater than rather than less than, takes the same stream of arguments, but instead of applying f to g to x, we apply g to f to x. So this is in some sense similar to piping or backwards composition. So we apply f to x and then apply g to the result of applying f to x. And as with composition, we can define this function also with one very simple line, and this function is too auto-curried, which means that we get all the benefits that we talked about before, meaning that we can construct a composition and then save that composed function into a variable, pass that around, and then run that function on different values multiple times. So here we composed inc and double and stored it in this variable we called f. Let's actually call this variable double then inc in order to make it a bit more explicit what's going on. And then of course we have to change this these f's to double then inc. But then we can construct a new function which we will call inc then double, and that will be there's probably a mathematically more accurate name for this, but I don't know what that is, but that will be the reverse composition of inc and double. So we pass the arguments in the same order, but we pass it to this function, this backwards compose function, or this, maybe I should actually call this forward compose, this pipe-like compose function. And if we then call that function, so let's change this. Here we call double then inc on 10, and let's here then call inc then double with the same number with 10. Then we can see that these two functions yield two different results. So this first 22 is from this JS-log statement. So we're interested in the two latter or two latest JS-log statements. The first one is 21 and the second one is 22. The first one stems from this line where we doubled first and then incremented, but the second one stems from the one where we incremented first and then doubled, which of course are different things, right? Because in this first one we first double, so we go from 10 to 20 and then we add 1. But in this second one we first increment from 10 to 11 and then double 11, which of course yields us 22. Now, we've only used the prefix notation, but as I mentioned, we've defined it using these special characters in order to be able to use the infix notation. So what's really cool is that we can now actually compose, we can do something similar to this. Let's call it f again this time. So we define a function f, which is inc composed with double. And this is equivalent to this. It's just a different notation. And we can then, so let's call this f1 and then let's call it this f2. And then we can do the same thing with the other compose operator. And these work exactly the same way. So similar to these lines, let's do the same thing, but using these two infix notation functions. We can say JS-log f1 on 10 and then JS-log f2 on 10, and we should get the same results. Again, we get 21 and we get 22. So these yield the same results as these. And what's really interesting about this is that you can keep on stacking on functions here. So now we are composing inc with double, and then with inc, and then with double. And again, because everything is auto-curried, you could define, let's say we define a function called molt, which takes an x and a y and multiplies x with y, which means that we can then use this within this composition. So we could say, here I want to molt, but I want to molt with 10. So because of currying, molt10 returns us a function where x have already been applied, but y has not. So then we can use it in this composition because we're simply missing the last y. And so forth and so forth. Again, let's not make this a video about composition, but this, in my mind, is really cool and actually really, really powerful. And of course, you can mix these two composition operators any way you want. The really important part here is that we get composition, we get pattern matching, we get all of these good things from functional programming while we have strong typing. So if you, for example, have tried to use the fantastic functional library Ramda with TypeScript in order to get static typing and the power of functional programming in JavaScript, you've probably noticed that it doesn't work as well as you would probably want it to. So the type inference in TypeScript is not as powerful as the type inference system of OCaml. So again, back to the point that we read here in the what and why section of the docs, where they say that the type system here is sound. So if it compiles, then the types are guaranteed to be accurate, whereas this is not really the case in TypeScript, if I'm not misunderstanding. So that means that you can do all of this crazy stuff that we've done here with the composition, but you can still rest assured that your types are okay, because if it compiles, they're fine. So anyways, those are my 5 cents about ReasonML. So if you want to write JavaScript but see the power of statically typed functional languages, then definitely check out ReasonML. And if you don't see the value of statically typed functional languages, I would humbly encourage you to check it out, because my humble subjective opinion is really that statically typed functional languages are really the future of programming. That's it for this, an introduction to. Feel free to suggest topics if you want me to do introductions to other things. Thank you super much for watching. Remember to subscribe for more videos about programming, and I will see you in the next one.